This is the second section of Chapter 13 in our dynamics textbook. The first section discussed the background for Newton's laws, specifically the Newton's second law that we'll be using for the rest of this chapter in a significant way. And so in this section we will be applying Newton's second law to determine forces and accelerations for particles in rectilinear motion or Cartesian coordinate systems. An example might be a person is pushing this large heavy crate, trying to move that 100-pound crate. How large a force must that person exert to start the crate moving? And then once it starts moving, what kind of acceleration will it have? And so how can we do those computations? That kind of a problem. Another is objects moving in air might have drag forces that attempt to change the velocity, of course. So how can we calculate things along those lines? In rectangular coordinates, we will of course be applying Newton's second law, assuming constant mass, so it appears outside of the derivative of velocity with respect to time. And so we have force is equal to mass times acceleration. The force shows up in bold yellow. The acceleration shows up in bold yellow, meaning that those are vectors, not simply scalars. But in Cartesian coordinates, it's very easy to break those into the three Cartesian equations. Force in the x equal mass times acceleration in the x. Same for the y, same for the z. Remember that it is these unbalanced external forces that will cause an acceleration of the body. So as I've just said, we can take that vector equation and break it into scalar components. So sum of forces is sum of forces in the x, the y, the z, all added together using ijk unit vectors is equal mass times the acceleration components, multiplying the I, j, and k Cartesian unit vectors. Or we can simply write them as three separate scalar equations. Sum of forces in the x equal mass times acceleration in the x, same for the y, same for the z. Our procedure, and this is critical that you always do a free body diagram. I will say again, I've worked lots and lots of dynamics problems. If I don't draw a high quality free body diagram, I've got about a 50-50 chance of getting the problem right. And so I suspect the same ought to be true for you as well, that you won't get the problem right many times if you don't draw the free body diagram. So on that free body diagram, we will establish a coordinate system, and drawing the coordinate system and in particular showing the directions of the positive coordinates is important on the free body diagram. Then we will draw the particle. We will show only the external forces within a given particle. Now, we might have two different bodies interacting, and we might want to separate those bodies and draw a free body diagram for each body. In that case, there will be internal forces of one body acting on on each other in those two different free body diagrams. External forces will generally include the weight of the body, normal forces from the surfaces they're resting on. Friction forces will often appear in these free body diagrams, and any externally applied forces by motors or humans or ropes or whatever else is happening. And we will show the MA vector, or the inertial force. We'll show that on a separate diagram called the kinetic diagram. Be very careful with friction, because friction always opposes an attempt of the body to move. The friction never assists the body in moving, and so it opposes relative motion between two surfaces that might be rubbing together. And we might also have particles that are connected to linear springs. Make sure you place any spring forces on there. Make note that those spring forces would be a k value times some sort of a displacement value. Once we have the free body diagram, we can write the equations of motions from the free body diagram. Again, we've already seen this Cartesian form. Breaking it into three scalar equations is usually the easiest way to go. Now, once we've drawn a free body diagram and we've written our equations of motion, that will give us a relationship between forces that are happening in the system and accelerations that are happening in the system. But that may only be part of the story for lots of problems. Once we've used the equations of motion potentially to find accelerations, the next part of the question might be determine the velocity or determine the position of the body after a certain amount of time. Well, that sounds like a chapter 12 kind of question, and it is. And so what we add to our dynamics toolbox is the equations to allow us to relate forces to get accelerations. And from chapter 12, we already have skills to relate accelerations to velocity and position, those other kind of kinematic variables. In addition, if we have constraints, like we have to follow a path, we have to incorporate those equations to solve the problem. And if we have coordinated motion between two bodies like pulleys, we also have to include those equations to come up with the total motion. So chapter 13 is not a chapter in isolation. It is a tool to let us go even further using chapter 12. So we have an example, and we have a box of a given mass, 20 kilograms, and that box is being pulled up this incline by a motor, and it's going to move a distance of s is equal to 6 meters, and it's going to do that in 3 seconds, and it will do that starting from rest with a kinetic coefficient of friction of 0.3. Now, a reminder from physics, two different coefficients of frictions between bodies. A static coefficient of friction would apply right up to the moment when the bodies start to move relative to each other. So static coefficient of friction is what's there when the bodies are not moving. It's generally larger than the kinetic coefficient of friction, and once the body starts to move, at that very instant, the coefficient of friction drops down to the kinetic coefficient of friction. We are presuming that this body will move, and therefore, during its motion, the kinetic coefficient of friction will be in effect. Our question is, what tension must there be in the cable? And if we know cable tension, then that would allow us in a next step that we're not going to do, to talk about motor torque and motor speed, and would allow us to talk about motor power. And from all of that, we would be able to choose the motor out of a catalog somewhere to be able to get this job done, because we would know torque, speed, and power. And we'd get to decide whether or not we need a gearbox to make this motor work. So our plan will be a free body diagram and kinetic diagrams. I am massively dependent on free body diagrams. I often personally don't draw the kinetic diagram. We'll talk about that, because it just doesn't, to me, it doesn't say as much. If it helps you, that's fantastic. We'll write the kinematic equation that will deal with acceleration, and we will then apply the equation of motion once we can say something about acceleration to determine the cable tension or the cable force. So let's see how this problem proceeds. We have a free body diagram. Notice our coordinate system, and we can pick any coordinate system we choose. If we have objects on incline, it is very often helpful to align our coordinate systems with the incline or with the slope. So I would call this a slope-aligned coordinate system, where x points up the slope and y points perpendicular to the slope. Our other choice would be to draw what I would call a gravity-aligned coordinate system, where the y-axis would be vertical in the direction opposite to gravity. The x-axis would be horizontal or perpendicular to the gravitational acceleration. We can draw either one we want, but sometimes problems become a lot easier if we use the slope-aligned coordinate system, because our forces, our accelerations are only in one direction quite often. So that's what we've done here. A great free body diagram should have coordinate systems with the positive directions labeled very clearly. Then we have the particle, and since our particle is rectangular, we're going to draw it as a block. And we have the weight of that particle acting downward. That particle is sitting on a flat surface, and there's a normal force between the surface and the particle itself. And we have a friction force that is pointed down and to the left. Why did we choose down and to the left? Because we have a rope tension that we are utterly confident will be pulling this box up the slope, and then so that it will acquire a velocity up the slope, and that friction force will be in the opposite direction of that relative motion, or in the opposite direction of the velocity of this object. Almost always, we're going to use a simple model of friction that says the friction force is equal to the appropriate coefficient of friction times the normal force, and here's the normal force. And the appropriate coefficient of friction for this problem, again, was given as the kinetic coefficient of friction, 0.3. We also put the rope tension on here, and several of these things are unknown, and we will write our equation of motion. It'll have some unknowns. We'll write our kinematic equations. It will probably have some unknowns, and then we will combine those equations. Hopefully at the right point we'll have n equations, n unknowns, and hopefully if life is good we'll never have more than one equation, one unknown, that has to be solved at any given time. Kinematics. We have this object sliding up the hill. Now, I don't remember if it said it clearly, but that rope tension is going to be a constant. Yes, the motor winds in the cable with a constant acceleration, and since we're moving in a straight line on a sloped surface, if the acceleration is a constant, the tension will be a constant, but we were told the acceleration is constant. Going back to our kinematics now, our acceleration is constant, and we were told that we would be traveling up the hill and that we would move 6 meters and during a 3-second time period starting from rest. These three numbers, moving 6 meters over a 3-second time period starting from rest under constant acceleration, will allow us to write an important equation. That important equation comes off our equation sheet from constant acceleration. This is the one we would call the position equation. I would note this equation is a little bit different than our equation sheet because there is an S final on the left-hand side. There would be an S0 or an S initial on the right-hand side, but we're going to call our starting S position 0, so we didn't write that variable right here because we put a 0 right there. And so this equation says our final position, 6, is equal to our starting velocity, 0, we started from rest, times time of travel, plus 1/2 the acceleration imposed by the motor times time squared. Time is going to be 3 everywhere in the equation. This is a one equation, one unknown problem that from the kinematics tells us that the constant acceleration has to have a value of 1.33 meters per second squared, purely from the kinematics. Knowing that acceleration, we can now turn to our equations of motion, which would come from our free body diagram. Looking first in the y direction from the free body diagram, we will see that we have a normal force. Well, first of all, note the y direction is slanted. We have a normal force coming from the surface that is sliding on that is purely in the normal direction. The friction force has no contribution in the normal direction, nor does the rope tension, but we do have the weight, which is acting downward. We were told that we have a mass of 20 kilograms, and this G is and maybe it's a touch misleading, this G is the value of the gravitational acceleration. So weight is equal to M times G, mass times gravity. And we have a component of the gravitational force in the y direction, but because our axes are slanted, there's also a component in the x direction. And if we're going to sum forces in the vertical direction or the y direction, we will have a positive normal force in the y direction, and we will have a weight times the vertical component. In this case would be the cosine of the 30 degrees. Why is that? Well, notice the 30 degrees is measuring the angle from the horizontal to the vertical. If we were to bring the 30 degrees over here, I said that wrong, 30 degrees from the horizontal to the slope. If we were to bring that 30 degrees over to this figure, we'd have a horizontal axis here and a 30-degree angle to that thing called t. And so the vertical, the y direction component in this case would be the cosine term. And let's just check that. What would the weight force be if our slope went to 0? Cosine would go to 1 when angle goes to 0. So the y direction force of gravity is the cosine term. Looking back here, so our sum of forces in the y direction would be the normal force, positive, the gravitational component, negative, because the diagram showed it pointing in the negative y direction, and on the left-hand side, our mass times acceleration, the other portion, because sum of forces in the y equal mass times acceleration in the y, but that acceleration component in the y direction is 0. The box never moves in the y direction. This is a one equation, one unknown problem. The only unknown is the normal force, and the normal force is 169.9 newtons. Notice this g right here has a value of 9.81. Then we can go back to the free body diagram and sum the forces in the x direction and set that equal to mass times acceleration. Going back to the free body diagram, in our x direction, which points up the slope, we have a positive t, we have a negative 0.3 newtons acting down times the normal force, 0.3 times the normal force acting down the slope, and we also have a component of gravity. Look at it very carefully. That component of gravity will be pointing back down the slope. The component of gravity will be 20 times g times the sine of the angle 30. And again, if that slope angle went to 0, our x direction component of gravity would go to 0. So the sine equation makes sense. Back to the equation of motion, sum of forces in the x equal mass times acceleration in the x. We had the tension force positive, we have the gravitational component is negative, and we have the friction component is negative. And the mass times acceleration we will write as 20 times that unknown, or times that acceleration in the x direction. Now, is that known or unknown at this point in this problem? In this problem, it is known. It is the same acceleration that the motor is providing. We've already solved for that acceleration, and it is 1.33 meters per second squared. So, plugging in everything that is known to the problem, T, the rope tension, is unknown. The G is unknown. The normal force is known at this point because we've just solved for it. The acceleration is known. The only unknown in this equation is the rope tension, and we solve for the rope tension as that only unknown, and we come up to 176 newtons. And that should end that problem. Well, yes, that would end that problem. Now notice in this case, we used known kinematics, acceleration, to determine the acceleration. Okay, our known kinematics let us determine the acceleration, and from that we were able to determine one of the unknown forces. In other problems, we may know all the forces from which we could determine the acceleration, and once we know the acceleration, we could use the kinematics then to determine other motion variables, positions and velocities. Next problem, very similar, but we're putting wheels on the problem. We have an ore cart with a mass of 400 kilograms. It has a starting velocity of 2 meters per second. We know the force in the cable is going to vary with time. That force is 3,200 times time squared, force in newtons, time in seconds. We want to find the velocity and the position of the cart when time is 2 seconds. This sounds very much like a chapter 12 problem, but we need to know the acceleration. We'll want to be very careful which acceleration equations we use. We'll have to determine whether acceleration is constant or not. We can conclude that right away. Since the force is not a constant, then the acceleration is not going to be a constant. We must not use the constant acceleration equations in this problem. So our plan is we have forces and velocity involved. We have both kinematics and the kinetics, or the equation of motion. We will draw the free body diagrams. We will write the equations of motion from the free body diagrams, and we will use the kinematic equations to determine velocity and distance. And we've already looked ahead to know that we will not be using the constant acceleration kinematic equations. The free body diagram, very important. Draw the coordinate system. Label the positive directions so that we can put appropriate signs on the terms when we write the equations of motion. On the free body diagram, we have the weight acting downward, the mass of 400 kilograms multiplied by the gravitational acceleration. We have the normal force acting in the upward y direction. We have the rope tension acting up the slope. There's no friction on this one because we have wheels on the cart. They are presumed to be frictionless, so there's no friction acting between the surface and the cart. Over on the kinematic diagram, we are saying to ourselves there is an acceleration that is acting up the slope, and it is the mass times the acceleration up the slope. There is no y direction acceleration showing. That is intentional because it only moves on the x-axis. And if it only moves on the x-axis, the acceleration in the y direction is 0. So writing our equations of motion, in this case, we have a normal force. Since there is no friction, there aren't going to be any needed unknowns. If we wrote the sum of forces in the y direction equal mass times acceleration in the y equals 0. There are no unknowns that we will need to solve for of any consequence. So let's first just write the equation in the x direction, and we'll see that we're going to solve for everything and never need to have written that acceleration equation in the y. So sum of forces in the x equal mass times acceleration in the x. The forces in the x would be a positive rope tension and a negative component of gravity, and that component of gravity would involve the cosine of this slope angle, but the problem statement gave us an 8, 15, 17 geometry, and so that sine term is going to be the 8 over the hypotenuse. Sorry, this is the x component of gravity is going to be that sine term, 8 over 15, x component of gravity, and all of that is equal to the mass times the acceleration. Sum of forces equals mass times acceleration. In this one, we know the rope tension will vary according to the equation 3,200 times time squared, leaving the only unknown in this equation to be acceleration. We solve this equation for acceleration, and after just a little bit of combining the numbers, we get that the acceleration is 8 times time squared minus 4.616. That's our equation for acceleration in meters per second squared. And quite clearly, acceleration isn't constant. It changes with time. But notice we learned our acceleration behavior purely from the x direction. There was nothing needed in the y direction. Now, what if friction were involved? If friction were involved, we would need to sum forces in the y direction to get the normal force. Knowing the normal force and the coefficient of friction, we'd have drawn our friction term here. We would have had a friction term both in the y equation and in the x equation, at that point it would have been important that we solve both the y direction equation to learn the normal so that we can learn the friction, and then we would have a friction term appearing in the x equation. No friction, that didn't happen in this problem. We know the acceleration up the slope as a function of time. Everything left in this problem is a chapter 12 problem. So, knowing that acceleration, if we want velocity, knowing acceleration versus time, we can integrate that acceleration, and integrating acceleration, we're going to get a final velocity is starting velocity from our limits of integration, okay, is equal to the integral of a dt, and integrating that, okay, we put in our initial velocity of 2, that was given in the problem statement. The integral of a dt between 0 and any particular time t, or general time t, is going to be a t cubed term. Okay, so an 8t cubed over 3 term, and a 4.616 times time, integrating that component. Both of those evaluated between the lower limits of 0 and the upper limit of t. It says that our velocity is 2 plus 8/3 t cubed minus 4.616 times t. Notice when t equals 0, these terms go away and our initial velocity is 2. At t equal 2 seconds, we plug in 2 seconds everywhere we have t, crunch the numbers, and we have a velocity of 14.1 meters per second squared. Now if we want to know where we're located at the end of 2 seconds, we'll take our velocity equation before we plugged in the t equal 2. We will integrate this equation, and we will have an s is equal to s0 plus the integral of velocity with dt, and our initial position we're going to call 0, and then we have to integrate our entire velocity equation, which was the 2 plus 8/3 t cubed minus 4.6 times t. We integrate all of that. We're going to get a t term out of the 2. We're going to get a t squared term out of here. We're going to get a t to the 4th term out of here. Integrating those, again, between lower limit of integration of t equals 0, upper limit of integration of t. Integrating those, there's the t term, the t squared term, and the t to the 4th term. That is our position equation. At t equals 2 seconds, plugging that into t everywhere, we come up with a position of 5.43 meters. In this case, the forces were known. They were a function of time, not constant, therefore acceleration was not constant. We had to use chapter 12 to do velocity and position. That ends this section. We now turn to chapter 13, solving problems that are most convenient in the normal and tangential coordinate system. In particular, just like chapter 12, when we know that we're following curved paths, those will either be cylindrical coordinate problems or normal and tangential problems. Sometimes one of the other is easier, sometimes they're both equally easy. And so this shows an example of a centrifuge that NASA would use to cause the astronauts to make very, very funny faces, if you've ever seen those videos, because of the centripetal accelerations that are going on. An application where normal tangential coordinates and kinetics, F equal ma, might be useful would be race cars traveling at high speeds on curved paths. It might be safe or safer if we in fact put a bank on the curved path to take control of forces and not have to have as much frictional force between the tires and the road to keep the cars from sliding sideways. Amusement park rides can often have very complicated motion, causing the riders to follow a very interesting path. And we might want to then determine the forces on riders, might want to determine forces between a cart and a track system. For a very poorly designed roller coaster, we might want to determine at what point the roller coaster car flies off the track. That would be a very unfortunate event that we as an engineer want to prevent. Another application, when satellites orbiting the Earth following what may very well be an elliptical orbit, might be elliptical, might be circular, the primary force acting on them is the force of gravity, and we can say things from that about the size of the orbit, the speed of the orbit, those kinds of things. Remembering the normal and tangential coordinate system, we would have a particle which is required to follow a path, and on that path, this might be a three-dimensional path weaving through three-dimensional space, and we will set up three coordinate vectors. One of them will be a tangent vector, which is tangent to that three-dimensional path. For a small segment of the path, even if it is located in 3D, we can fit a perfect circle, a best perfect circle, to that 3D path. That circle might be tilted in 3D to some extent, but that circle will have a center, and our normal coordinate unit vector will point from the particle toward the center O of that circle. That is, and it is a circle that is in a plane, but that circle may be skewed in 3 dimensions. So we have our tangential coordinate unit vector, our normal coordinate unit vector. Perpendicular to that, we would have the binormal unit vector. If we're dealing with planar paths, then we will simply ignore or leave off this binormal vector. And in just a moment, we'll say in the notes that there aren't going to be any accelerations happening in that binormal direction, because that would cause us to leave the path if we did. So normal direction always points toward the center of curvature. There is a right normal vector, a correct normal vector. Pointing it in the opposite direction would be wrong, and it would get wrong answers from the equations. And since we're using Newton's second law of a vector equation, sum of force vectors equal mass times acceleration vectors, we can write that in normal and tangential coordinates by saying sum of the forces in the tangent multiplied by the unit tangent, the normal direction forces multiplied by the unit normal vector, and the forces in the binormal direction multiplied by the binormal unit vector is equal to mass times the tangent acceleration plus the mass times the normal direction acceleration. Notice there is no binormal acceleration, and that is because any motion in that direction or acceleration in that direction would cause us to leave the path, and if the accelerations are zero, then those sum of forces in the binormal direction are also zero. We will then take what's left out of this equation and typically just break it into components and look at sum of forces in the tangent direction equal mass times acceleration in the tangent, and sum of forces in the normal direction equal mass times acceleration in the normal. We'll say whatever we can that is true by writing these normal tangent equations of motion. Then we also have all of the kinematic skills we learned in Chapter 12 related to the normal and tangential directions, which may require to solve interesting problems. Remembering some of that kinematics, let's first of all recall the tangent direction acceleration a sub t is rate of change of velocity with respect to time. And remember, the velocity direction is only the velocity vector is only in the tangent direction. So probably a better way to say this is this tangential acceleration is the rate of change of speed, or of the magnitude of velocity, magnitude being the key word right here, rate of change of magnitude of velocity, or rate of change of speed. That would depend on tangent direction forces. In the normal direction, we know that the normal direction of acceleration is always v squared over rho, and that's an acceleration related to the change in the direction of velocity, always acting inward. So the sum of forces in the normal direction will always be set equal to mass times acceleration in the normal direction, and which will then be set equal to mass times v squared over rho. We'll see that in a moment. Remember that that row term, radius of curvature, can be calculated from dy dx, a space derivative, not a time derivative, and the second derivative of y with respect to x, a space derivative, not a time derivative. And of course, to solve these kind of problems, our normal tangential is useful when we have motion along a curved path. We will choose our normal tangential coordinate system properly. We will draw free body and kinetic diagrams properly by very carefully putting on the free body diagram the normal and the tangential unit vectors. We will show the definitions of the positive direction vectors, and then we'll write the equations of motion, and then we'll apply any kinematics that are necessary. Part of the kinematics might be that the tangential acceleration is in fact dv dt, okay, but it also might be in an ADS equal VdV way, that the acceleration is equal to v times dv ds. And the kinematic relationship that the normal acceleration is v squared over rho. But this thing implies we might be doing some integrating or taking derivatives to relate accelerations to velocities or positions. So in an example, a 10 kilogram ball has a velocity of 3 meters per second when it is at point A. Notice point A is located 45 degrees down from the horizontal, okay, and it's moving along the vertical path. This circle is not happening on a flat table. This is more like a Ferris wheel where we are rotating in a vertical plane. This would be very much like a person on a very exciting swing if they ever went to the top part. What we want to know is the tension in the cable and the tangential acceleration, or the increase in the speed, the rate of increase of the speed of the ball. That'd be the tangential acceleration. Since we do in fact have a curved path, normal tangential is a candidate. We might possibly consider cylindrical coordinates in the next section. Right now we'll use normal and tangential. We'll draw free body diagrams, we'll write the equations, and see what turns out. I will point out that this is a simple version of a more interesting problem, because they did not ask us to say anything about the ball continuing to move away from theta equal 45. If they did, let me scare you a little bit. The tangential acceleration is driven by gravity, and gravity alone in this problem. And as we change theta, the intensity of the gravitational acceleration in the direction of the motion of the ball goes downward. That acceleration, tangential acceleration, would change with theta. Theta would change with time. And so figuring out how long it takes the ball to get to the bottom, figuring out the speed of the ball when it gets to the bottom using this kind of a coordinate system is a really interesting problem. I will probably create a video in a little while that illustrates solving the problem, but I'll probably put a child on a swing and solve it that way instead. But that's not involved here. That makes this a much easier problem. We simply want to know the tension in the rope and the tangential acceleration. And so we draw our free body diagram. Here is our particle. Our weight is acting straight down. Our rope tension is acting inward toward the center of the circle. Notice we have our normal unit vector pointing in the correct direction toward the center of the circle. We have our tangent unit vector pointing tangent to the path and in the direction that the particle is moving. The kinematic diagram says we have two mass times acceleration terms. We have a normal direction mass times acceleration term and a tangent direction mass times acceleration term. And so we'll be writing equations that say sum of the forces in the normal direction equal mass times acceleration in the normal, and sum of forces in the tangent direction equal mass times acceleration in the tangent. Two different equations and probably some kinematics involved as well. So sum of forces in the normal direction is mass times acceleration in the normal. And looking back, we're going to see that the rope force is in the positive normal. And we'll look back in a second and see that our gravitational force in the normal direction is in the negative normal direction. It's a W times the sine of 45 degrees. Looking back, our tangent force is in the positive normal direction. The component of this weight force, if we took the weight force and projected it along this line, that arrow would point in the negative normal direction. With the 45 degrees, we don't have to worry about whether we're talking about sines or cosines of 45 degrees because they amount to the same thing. So, two forces in the normal direction. Moving back, two forces in the normal direction, one positive, one negative, equals mass times the acceleration in the normal direction, which we know is v squared over rho. And let's see, what were we? Okay, and we know the velocity at that point was 3. That was given in the problem statement. Radius of curvature of 2, given in the problem statement, although I didn't highlight that. We know that the weight is mass times acceleration of gravity. Mass was given as 10, acceleration of gravity 9.81. And what do we have left in this equation? We know the acceleration, v squared over rho. We know the weight, mg, then times sine of 45. Tension is the only unknown thing, and the tension in the rope is 114 newtons. Now, one thing to notice real quick. What does this object weigh? It weighs a mass of 10 times 9.81. It weighs 98.1 newtons. Our rope tension is higher than the weight. Why is that? It's because of that centripetal acceleration. Summing force in the tangent direction is mass times the acceleration in the tangent direction. Okay, and the forces would be a weight term, and that's the only term is a weight term. Jumping back, looking at this, in the tangent direction, the weight has a component that will be in the positive tangent direction. The rope force has no component in the tangent direction, so only the weight term alone. So positive weight times the cosine of 45 degrees equal mass times acceleration in the tangent direction. And we know the weight. The acceleration in the tangent direction is the only thing unknown. We solved that the acceleration in the tangent direction is 6.94 meters per second squared. And we have just solved this problem for the two requested pieces, the rope force and the rate of change of speed. Next problem, we have a car traveling over a hill. The shape of the hill is a parabola given as y equal 20 times the quantity 1 minus x squared over 6400. When the car reaches point A, which is 80 meters away from the crown of the hill, it has a velocity of 9 meters per second, and it has an acceleration of 3 meters per second squared. We are neglecting the size of the car. There's no rotations or anything like that to worry about. What we want to know is what is the normal force between the car and the ground, and what is the frictional force. And that frictional force would be exerted by the tires, between the tires and the road, to cause the car to be able to accelerate in its tangential direction. We will learn that normal force, and we will learn that friction force by applying the equations of motion in the normal tangential direction, and we'll apply any appropriate kinematics. I want to point out one very interesting thing in this problem. Because we're traveling on a curved path, and it's easier to see if we imagine the car back here heading up the hill. I think you can imagine a situation where the car is going so fast it will refuse to stay on this path, and what will happen is the car will in fact start flying through the air. Why does that happen? Because there is no pulling force possible between the car and the road. And of course, for me growing up, that was a Dukes of Hazzard experience. You see the Dukes of Hazzard TV show, their car going over hills and flying through the air. Or if this were a motorcycle, I'd have to talk about Evel Knievel, who we at times nicknamed Stupid Canoopid. But Evel Knievel would use hills to fly through the air. So what's going on in a problem like this the instant before the car flies into the air? Well, what happens is the normal force between the car and the road goes to zero. Right before it flies off the hill is supporting the weight. The instant after it's flown off the hill hill couldn't possibly support the weight of the car. That transition period from where it's on the hill to leaving the hill happens when the normal force goes to zero. If you're ever asked to determine at what point or at what speed does this car fly off the hill, you will use the idea that normal force has gone to zero. And I will probably work an example of that kind for you. So again, car follows a path. We want to know the normal force, and we want to know the friction force which allows us to accelerate. Drawing our free body diagram, we have the car. We have our very carefully labeled tangent direction shown positive, our normal direction shown positive. If we leave these directions off the problem and just off the free body diagram and just drew the forces, we would have an incomplete free body diagram. Notice the normal direction must point down and to the left, because down and to the left is where the center of that approximating circle would be. We would get wrong answers if we allowed the normal direction to point up and to the right. The forces acting on the car would be the weight of the car, a normal force between the ground and the wheels, a friction force between the ground and the wheels, and that would be all of our forces. Then over on the kinetic diagram, we will have a mass times a tangential acceleration, and we will have a mass times a normal direction acceleration. And of course, the weight of the car will be the mass of the car times the gravitational acceleration. I think that's everything we need to say about that. And so we will then turn to summing forces in normal direction equal mass times acceleration in the normal, summing forces in tangent. Let's look at what will happen in the normal direction. We're going to have the normal force as a negative force. We'll have the weight force as a positive normal force. And those are the only things acting in the normal direction. In the tangent direction, we'll have negative friction and a positive weight component. Let's go look at those. Sum of forces in the normal, mass times acceleration in the normal. In the normal, we have a gravity component, and we have a negative road normal force component equal mass times acceleration in the normal, but the acceleration in the normal is v squared over rho. And a weight, of course, is mass times acceleration of gravity. Plugging those two pieces in, we have a weight term, which is totally known. Let's see. Actually, no, weight will depend on the angle theta. We haven't dealt with the angle theta yet. We'll come to that in a little while. And then we have the normal force, and then we will have mv squared, 9 squared, divided by radius of curvature. Right now, we don't know theta, and we don't know rho. Therefore, we don't know the normal force. As soon as we can use geometry to find theta and rho, we'll be able to conquer this equation and solve for the normal force. When we sum forces in the tangent direction, we have a weight component again, and that was acting in the positive tangent. We have the friction force component, which is acting in the negative tangent direction. That's equal to mass times acceleration in the tangent. We were told early on that the rate of change of speed was 3. That 3 is the tangential acceleration. We'll substitute that right there. We know the weight term. In this equation, we will then solve for the unknown force from the tires. That force is 7848 sine of theta minus 2400 is the way the algebra works out. Notice again that the angle of the angle theta, which is the angle of our slope, is unknown. We will have to find that. How will we find that? And how will we find the radius of curvature? Radius of curvature, you know, we have a big ugly equation. The angle of the slope is very much like a couple of the quiz that we just did, where we know the path. We can take the derivative of the path equation to get the slope value, and we can do inverse tangent of the slope to get the slope angle. And so, determining the radius of curvature by taking two derivatives of y equal f of x. In this case, y is 20 times 1 minus x squared over 6400. This is y equal f of x. Remember, we're taking dy dx. No chain rule in this one. It's just the simple derivative, and that's going to be a minus 40x over 6400. And then the second derivative will be the derivative of that with respect to x, which will just be a minus 40 over 6400. Plugging in x equal 80 from the original problem statement, that was our location. We then get a number for the first derivative, a number for the second derivative. Plugging those numbers in to the radius of curvature equation, we get a radius of curvature of 223.6 meters. That takes care of the row piece for our current location. Now we want to know the angle of the slope of the curve from the horizontal, and of course the slope of a curve is dy dx, but dy dx is the tangent of the slope angle. So we'll take dy dx at x equals 80, and that value was apparently 0.5 from, we saw that up here. And then we will take the inverse tangent of the negative 0.5, sorry, not a positive 0.5, inverse tangent of the negative 0.5. We will get 26.6 degrees for the slope of the curve. And then we take the rho value, plug it into the normal force equation. We get 67.28 newtons when we plug in rho and theta. When we plug in theta of 26.6 degrees into the tire force, tangential force, we get 1114 newtons. Now, an interesting thing to ask is, how does the normal force compare to the total weight of the car? Let's go back and look at that. What was the total weight of the car? Let's see, we had that somewhere. Okay, weight is equal to m times g. I've already forgotten the number, so let's go back and look at that. The mass of the car is 800, and g, so m is 800, g is 9.8. That's almost 10. So the mass of the car is just a little bit less than 7,000 newtons. What did we come up with for that normal force? Normal force of 6,700. Our normal force is less than the weight of the car for two reasons. One reason is because we're on a slope, the normal force doesn't feel the entire weight of the car. But the other is, part of that centripetal acceleration is making this car lighter as well. And at the right speed, it is conceivable that that number could in fact go to 0. That wraps up the problems in the slides for this normal and tangential section. In another lecture, I will be doing the cylindrical coordinates, but this is sufficient to get you ready for the homework that is due and over which you will be quizzed on Monday.